Hello everyone. Yeah, physics book tour, 2 weeks into school, third week just started. Here's the thing. So we're gonna start with some Coulomb's law. This finds the electrical force between two charges. You know how like positive and negative charges attract and like charges repel. Well, this basically finds the force that does that. And here's Coulomb's constant, which is this K over here, and Q1, Q2 are like the values of the charges, and R is the radius, and F is the force. And charges are in coulombs, which is like newtons, whatever, meters. It's just the SI unit. So yeah, this is the electric field. It's like how gravity attracts things. You know how gravity attracts masses, how things fall to ground. And this is basically the same thing, but for charges. And unlike gravity, there's also like charges repel, so it also like considers that into the question. So basically, yeah, the electric field is any charged object generates an electric field, and if you place another charge into it, a force acts onto it, and you can find that by taking the electrical force that we just found and divided by the charge. Q denotes the charge. And yeah, and we can also say like for a single charge, big Q, say this is a charge, like say this pencil is a charge, even though it probably doesn't. We can find the magnitude of the electric field at a certain radius using this equation. And yeah, K once again is Coulomb's constant that we just saw earlier. And yeah, here are some more notes about it. And here's basically talking about how electrical force can be transmitted through friction, induction, or conduction. So friction, obviously rubbing against each other, it transfers electrons. Only electrons can be transmitted, protons cannot be since they're larger. And we can also use conduction, which is basically by contact. And yeah, you know how like water is a conductor, it's basically like that, how like a charge flows through it, nice. And induction is a bit more special because you're not actually touching the thing. So say we have this neutral sphere, and then we hold a positive charge next to it. So what happens is if we once we hold it near, right, the electrons inside this neutral thing actually separate, since the negatives are attracted to the positive thing here. So all the negatives end up on this side. So this side, this half becomes negatively charged, while this side becomes positively charged. And if we somehow cut open this thing in half, you get two separately charged objects, which is really cool. And this process is called polarization. Anyways, Coulomb's law, once again, just like classroom notes, that's one's chapter's notes. And yeah, here's some more, just some more practice in general. Got some more practice problems, practice problems. Got a few. Yeah, these questions where they're in triangle is like a really good example of how like Coulomb's law, like electrical force is actually a vector, which means it has both magnitude and direction. So notice how I'm splitting the components into x and y components and combine them together to find the resulting vector. And it's kind of like how we use forces in physics 1. So yeah, here's some more examples. And finally, more electrical fields. Just as we talked about earlier, it's anyways, here's the newest one, which is called electrical field lines. This looks really scary, but it's just a way of visualizing the electrical field of an object. A positive charged object has fields radiating out of it, and a negative charge has stuff converging into it. And if we have a positive and a negative charge, we can see that these lines go from the positive to the negative, which kind of shows how the direction of electrical field. Although it's not pictured, every single one of these lines will eventually curve all the way over there, and with some special exceptions. And here's a similar one for two positive charges. Since like charges repel, you can see the lines kind of repel each other, they won't touch. And another neat thing is that the more densely packed these lines are, the stronger the electrical field there. So you see at A, is really densely packed, so that's where the electrical field is the strongest. B is slightly less densely packed, so it's weaker than A. And C, there's like nothing here, so there's a really weak electrical charge, if there even is any. Sorry, not charge, force. I think it's force. Yeah. So anyways, here we go. Here is an example. Here we have a 2q charge and a negative q charge, meaning that this plus charge is double the magnitude of this negative charge, which means that only half of the lines stemming out of this will actually reach the negative charge. And the number of lines stemming out of these charges is directly proportional to its value. So two equal charges, like we saw earlier here, have the same amount of lines coming out of it, whereas this one has double the charge value, meaning it has double the lines, and only half of them reach here, since this is only half the value. So yeah, here's some conductors. Conductors are basically stuff that conduct the flow of electrons. So yeah, here are just some characteristics of isolated conductors where like everything's in electrostatic equilibrium, where no net motion of charge occurs within the conductor. So yeah, here's some examples, and here is Faraday's ice rod experiment, which is actually pretty cool. So here we have a neutral conductor. This is like an ice pail, and here is a negatively charged sphere. And once we put the sphere here, remember how we talked about insulation slightly, where like the positive charge are like attracted here, right? So basically what happens is as the negative charge is lowered in, the positively charged, the negatively, so only negatively electrons moved, they move to the outside since they're repelled by the negative sphere. What occurs is that the outside is now negatively charged, and there's a reader here, it detects that and it detects a negative charge. Now, what happens is once the sphere touches this, all the positively charged objects, they flow into this I forgot the sphere's conducting. So this sphere conducts all of that positive charge, and now it's neutrally charged. And what happens when all the positive charge here are gone? This pail becomes from neutral into a negative charge. And now even when the sphere is taken away, this pail becomes negatively charged. And a really cool characteristic about conductors is that every single time excess charge is introduced, it always goes to the surface, because the charges inside the conductor always repel the excess charge up to the surface. And that's why when lightning strikes a car, you are safe inside, because all the electricity does not flow in, rather it stays on the surface. And here's some more homework. And yeah, here's some, just called electrical potential energy, and I'm not going to go over it because I honestly don't understand it perfectly myself. So yeah, here's just a quick flip through of all my notes. Basically, yeah, potential energy is like, I actually have no idea. The teacher hasn't gone over it in class, but here's some more notes. So yeah, what did we go over today actually? What did we go over today? I think we just went over what did we go over today? There's like I can't find it, shoot. It was the electric fields, weren't they? Wasn't it? Yeah, it was the electric fields. Here's some more, you can see like the drawings here. Yeah, pretty cool. So here's the physics notebook tour.